Okay, and thanks for having me. The photograph. Well, first of all, I want to just mention the names on the left here. This is the talk I'll be giving is over 30 years of research. Most of that work was done by my students, not me, and so some of whom are in this room tonight. And so I've listed the people that are have been involved in that research just to bring recognition to them. And I would also like to point out that a number of these folks are now at other universities where their faculty members have their own research programs, uh, including LSU, where my granddaughter just started college. So I'm a Tiger fan now, I guess. The photograph that you're seeing here was taken about a couple miles from where I grew up as a kid, a place called Fort Morgan, Alabama. I don't know how many of you are familiar with Fort Morgan, but it's a little bit like Bolivar Peninsula. My father was a party boat fisherman. It was sort of his dream. It didn't work out financially, so we had to move on to other things. But when I was a kid growing up here, all that light colored water you see was land. And those pine trees were well inland. So this was sort of my stomping grounds when I was growing up. Okay, let me make sure. All right. Space bar maybe? That'll do it. Okay, so we're going to talk about sea level, but you can't really separate sea level effects on coastal evolution from thinking about other things like sediment supply, which is largely controlled by climate. But let's talk about what sea level's done. The figure on the left actually have one of the best sea level curves anywhere in the world, Holocene sea level curves from here in Texas. There's a good reason for that, and that's because our shelf gradients are ideal. We have a lot of sediment out there. We have preserved banks and shorelines. So really good records come out. And I think a lot of that credit goes to the folks at Tulane, Tor Tornquist and his students who have done a lot of the work. But you can see we've got a curve that shows that if we go back about 10,000 years, the early Holocene, 10,000 to 7,500, that the rate of sea level rise was about 4 millimeters per year, which includes those pulses of rapid rise, which are caused by breakup of the big Antarctic ice streams. We now know, we didn't know that just a few years ago. And then that was followed by a decrease to about 1.4 millimeters, and then a half millimeter per year on average for the last 4,000 years. And that's the time interval over which our modern coast formed. So the barrier islands, the deltas that make up the Gulf Coast today, mostly were formed in the late Holocene, last 4,000 years. Now the real wake-up call here is if we look at the record for the historical time on the right here, it starts in the year 1900 and goes to present, or 2020, and it's the reverse of that long-term curve. So you can see that between about 1900 and 1940, World War II era, the rate of rise was 0.6 millimeters per year. Between 1930 and 1992, it was 1.4 millimeters per year. And then more recently, it's been up around 3 millimeters per year. But all of this happened within 120 years. So what we've done is we sort of reversed that 10,000 year rise in a matter of about 120 years. So we're back to the early Holocene. Welcome to the early Holocene. And so what we're going to talk about tonight is what was the Earth like, or what was the Gulf Coast like during the early Holocene and as we transition into these other times. Now there's an event at the top there. You can see those rates of 10 millimeters per year. That's actually unique to the Gulf of Mexico, and I'll talk about that more in a minute. But why is sea level accelerating? And we really know the question. To answer that question, a lot of people have worked on that. Well, one is the oceans are getting warmer all around the globe. The Gulf of Mexico is no exception. And the figure on the right shows the increase in surface water temperatures in the Gulf of Mexico using June. June is the datum here over the last 100 years or so. And you can see that since about the again, World War II era, the warming, the Gulf has been warming significantly. If you take the amount of warming and you do it's not simple calculation, but you do a calculation, you can convert that into sea level rise, and it comes out to about 1/3 of the current rate of rise. The other component of sea level rise are mountain glaciers, like the one shown here in Alaska. My wife and I went to Alaska last year, did a road trip. We wanted to go back one more time. We've been there before because we wanted to see some of these glaciers while they were still there. And we visited a few locations where we'd been in the 80s where there were glaciers and they're not there today. So this is actually a figure that's put together by the World Glacier Monitoring Service using state-of-the-art satellite altimetry and other satellite data that enables them to actually monitor changes in mountain glaciers over yearly and decadal timescales. And what it shows is a steady decrease in the volume of those glaciers. If you take that decrease in volume, you calculate its contribution to sea level rise, it's about 1/3. So now we've got 2/3 of our observed acceleration of sea level rise for the last 100 years, or most of that last 50 years, accounted for, and we only have another 1/3 to go. And we account for that with ice sheets. They're the 800-pound gorilla in the room. If we look at the volumes of the current ice sheets, they're actually capable of raising sea level about 200 feet. Now, that's not going to happen anytime in the near future, but the point here is that you don't have to change the volumes of these ice sheets to significantly influence overall global sea level rise. And in fact, the calculations, the best we can do in terms of calculations, indicate that that's accounting for that other 1/3 of the observed rise that's not accounted for by warming of the oceans and melting of mountain glaciers. That's a lot easier to do for Greenland because Greenland, the ice sheet stops short of the coast. So we can actually watch the margin of the ice retreat inland over years and decadal timescales. And that's what the slide on the left shows, the pink area. That's actually areas that have not deglaciating, but where nunataks or mountain peaks are starting to poke up out of the ice in more recent times. So we can measure the height of those features and actually get a pretty good feel what the elevation of the ice is. And of course, more recently, we have satellite altimetry that's capable of measuring these changes literally at centimeter resolution. Antarctica, which is most of that contribution to sea level rise, is a little harder to deal with because the ice is extending out into the ocean, and it ablates by producing these big icebergs that then drift away and melt. There's also meltwater at the base of the ice. It flows out under the ice into the ocean, so we can't observe those things very, very well. So it's a little bit harder to gauge the degree to which the Antarctic ice sheet is contributing to sea level rise and to estimate the rise in the future. There's been some papers not too long ago where people argued the Antarctic ice sheet's actually getting bigger. You might have seen those. I'm referring to the East Antarctic ice sheet, and they refer to satellite altimetry measurements that show that the ice sheet actually does sort of go up and down centimeters over years. But that's not really important to us because it takes that ice those changes about 100,000 years before they manifest themselves at the coast. It's in the West Antarctic sector in particular, these red areas, which are the big ice streams, areas of convergent flow, where most of the melting is taking place. And that's why scientists are focusing on those areas. Now, I mentioned earlier the rapid increase in sea level rise that's occurred in the last few years. And if you look at that curve, you'll see there are actually several blips on that curve where sea level went up and went back down again. That's not ocean warming. That's not glaciers, because glaciers don't expand and contract that fast, and the oceans don't heat up and cool off that fast. It's oceanographic effects, and we know those effects pretty well in the Gulf. We have this one current that's coming up from the Caribbean to the Yucatan Straits is called the Gulf Loop Current, pushes water into the Gulf, heats the Gulf more, and that results in these spikes in sea level. And at other times, the water kind of contracts. So that effect has been well known for a long time, and it's believed to be the reason for that sudden increase. Now, with that said, there are those who would argue that if we look at the deglaciation of West Antarctica, the first place the water that comes from the Thwaites Glacier, which is the one you've read about, perhaps Doomsday Glacier, first place to see that sea level rise is the Gulf of Mexico. So when the Antarctic melts, that water's not being distributed uniformly around the globe. There are places where, for various reasons, that water goes first, and the sea level effects are impacted first. And the Gulf of Mexico is the first place to actually see it. Now, NOAA is the agency that is responsible, the government agency in this country, for looking at rates of sea level rise, doing predictions, and constructing maps that show what the impacts of sea level rise will be. And they do a pretty good job. This is not the old bathtub model where you just take topography and flood it. They actually look at subsidence, and they look at a variety of variables to come up with these records. What you're seeing here, the areas in light blue are areas that will be inundated by the year 2050. My grandkids, who are in junior high and senior high right now, when they reach middle age, this is the world they will live in. And I think that's an important thing that we all need to recognize, that, yeah, the Earth's changing fast. 30 years is going to be a lot of changes. And those changes are happening now, as we'll see. It's not like it's going to happen next year. It started already. And so this is just the projections from the IPCC panel. And it shows that over the last 90 years, approximately, we've had about 1 foot of sea level rise. Sorry for switching back and forth from millimeters to feet. And that's about the magnitude of rise that we expect to see by the year 2050, because the rate of rise, again, is accelerating. That is without any increase in the contribution from the Antarctic ice sheet or the Greenland ice sheet. We now know that the Greenland ice sheet is, in fact, melt rates are accelerating, and we know that the Antarctic is showing signs of acceleration. Now, as geologists, we know that that's not the norm. I mean, when you took earth science, regardless of when you took it, you probably saw maps like this that showed the growth of the Mississippi Delta over the last 4,000 years. As it formed these huge delta lobes that grew out to sea, eventually they were abandoned and reworked. Those maps date back to the years of Fisk and his colleagues. And so it's been a real long time. This is nothing new, but it is telling us that the present NOAA prediction on the left here is by no means, it's a reversal from the long-term pattern. Now, it's important also to recognize that sea level is not the only thing affecting our coast. Climate is important, and particularly as it controls precipitation, as it controls river discharge and therefore sediment supply from the larger rivers. And in Texas here, we're living in kind of the hot spot in terms of climate impacts, because if you look from Key West, Florida, around to the Texas-Louisiana border, you see that precipitation is fairly high. And so not much has changed, even if we look at tree ring data and paleoclimate data. That's pretty well been the case, as we'll see later. However, Texas is in this region where we're seeing a major gradient in precipitation from the Louisiana border down to the Mexican border. And so that's telling us that in the future, we need to also think about climate change and how that might affect some of these things. Well, what do we know about climate change in Texas? The slide on the left is sort of a global, just background slide to show you that since about, well, since the Holocene began around 11,000 years ago, there was this fairly rapid warming that took place. And then we came into the Holocene world where temperatures didn't vary a lot, but they've been actually cooling through most of that time, right up until about 200 years ago. And then the curve on the right, B there, that's the last 200 years. That's what's commonly called the hockey stick, which shows the dramatic warming that's happened in the last 200 years. And of course, that parallels the doubling or tripling of CO2. Now, the slide on the right, the upper slide there, is actually a record that goes back, that shows precipitation in the Rio Grande Valley, which goes up into Fluvial Valley, which goes up into Colorado. And what it shows is that in the green line there is a number of ups and downs in precipitation. And some of these events, some of the more recent ones, the 1892 and 1993 and current drought events, are well known. They're well documented in historical records. So the Rio Grande has a history, natural history, before humans even came on the scene, of up and down sort of drainage that was connected to changes in precipitation. The bottom slide is from Nielsen Gaiman, who's the state climatologist, and models that he ran that show that what's expected in the near future and what's happened in the recent past. And it should be, the colors aren't coming out very good here, but it should be some yellows and pinks there, or some pinks there, that show that the models suggest that it's going to get more arid in the western U.S. Well, has this affected the rivers and their sediment discharge? The slide on the far left and this slide here show these big delta headlands that extend out into the Gulf, one associated with the Rio Grande River and another one associated with the Brazos, Colorado River, that sort of indicate, well, there was a time when these rivers were producing a lot of sediment to produce these big headlands. In fact, we know that if we go back far enough in time, in Holocene time, that the Rio Grande, the Colorado, and the Brazos River actually produced big fluvial-dominated deltas out there on the shelf. And we've mapped those deltas, and you can see the cliniforms and see that they were low bait, they were shifting around, so they were clearly fluvial-dominated deltas. This was before the late Holocene. If we look at what's happened in more recent time, in the case of the Rio Grande, slide on the upper right, that's 1854, and in 1854 there was a wave-dominated delta there that was about the size of the present-day Brazos Delta. And then the slide on the lower right here, this slide here, shows the mouth of the Rio Grande today, and that delta's gone. So there's another delta you can chalk off the list, the Rio Grande. It was an active delta in the 1850s. It no longer is. The same can be said for the Colorado Delta, which is now a bayhead delta. It used to produce a much larger delta out there on the shelf. And the Brazos Delta. Now, the Brazos Delta has been altered. Its course has been modified by shifting the. Well, let's step back a second here, and it's important to recognize that the Gulf Coast is not just deltas. It's made up of multiple coastal environments, barrier islands, deltas, estuaries, wetlands, a whole range of different coastal environments that respond differently to sea level rise. They don't all just sit there and allow themselves to be drowned. They all have different response times. So what's happening to deltas may not be the norm. And the question is, well, what's happening to these other coastal environments? This is actually shows these myriad of coastal environments with their different response. And so what we really want to know is how's the coast going to respond to changes in climate, changes in sea level rise over the next few decades. And this just shows that most of our coast, the Gulf Coast, is made up of barrier islands and deltas. And then, of course, there's the Chenier Plain near the Texas-Louisiana border. And I should also mention subsidence. I'm sure by now some people are starting to think, oh, you haven't mentioned subsidence. But of course, subsidence is important. We have to add that to the eustatic rise in sea level to get the true rise, the relative rise. And this figure on the left here shows locations where tide gauge records exist that go back at least 50 years. And then the figure on the right is a figure that was put together by a group from Louisiana looking at rates of subsidence. And again, sorry for changes in the scale here. Rates of subsidence in the numbers, starting at 0.7, going to 2.3. And as you look, you see those numbers increase toward the coast, towards the Gulf. And the dashed lines are actually the thickness of Holocene sediments. So what the group at Tulane University in particular has discovered is that it's the compaction of Holocene sediments that accounts for more than 80% of the subsidence that they're seeing over Louisiana. And we might think, well, if that's true for Louisiana, why should it be different from Texas? Except, of course, we don't have this huge big delta out here. But we do have bayhead deltas. And bayhead deltas are important because they are the nursery grounds and the nutrient sources for our estuaries, which are the nutrient sources for the Gulf of Mexico. And so they play a vital role in the Gulf of Mexico ecosystem. And this slide just shows some of those larger deltas. The Mobile Delta, for example, extends about 50 kilometers north of Interstate 10. So it's a very large delta. Most of these deltas are within 1 foot of sea level. And that's because actually during the last 3,000 years, remember sea level has risen very slowly. So these deltas have been able to grade and flatten out more or less, produce these very flat delta plains. They're now highly susceptible to inundation by rising sea level. So it comes as no surprise that when you look at, again, NOAA models, Mobile Bay in 2050, the delta will be up near Interstate 65, where it crosses that delta, several tens of kilometers to the north. Trinity Delta here in Galveston Bay, it'll shift about 10 kilometers to the north. And it'll stop there because of topography. There's some Pleistocene topography that will slow it down. The area between Sabine Lake, Calcasieu, it'll be inundated. Nueces, it'll be inundated. So these bayhead deltas are going to see some significant changes over the next few decades. How does that compare to what was happening a few thousand years ago? Are these rates that we're talking about now, are they, if you just think about it, simple math, these deltas could not have been retreating at these rates for thousands of years because, they just have not moved that far. But we can actually do better than that. The slide on the left shows seismic facies that occur within these deltas. And much like offshore deltas, you have very distinctive cliniforms. And you have flat-lying strata that represent bay sediments, and cross-bedded strata that represent the lower bay tidal influence sediments. And also, when we take cores, we can see that there are differences in the sediment types, the sedimentary facies, and big differences in the fauna. For example, Rangia here, which is known to be very abundant up on the Delta Plain, but it doesn't live in Galveston Bay, and it doesn't live that far inland. So it's a kind of a good sea level marker for those deltas. So we've looked at those bays, we've looked at Mobile Bay, we've looked at altogether 8 bays over the years to see how these bays evolved over the last several thousand years compared to what's predicted. And The slide in the middle here shows our data that the red line, and the dark line, black lines represent seismic data. The final black lines represent USGS lines that were shot back in the 70s, and those aren't very helpful for seeing the internal stratigraphy of the bay, but they do show very nicely the Pleistocene surface, so that we can get a map of what the topography of the bay, the antecedent topography, looks like. And from that, we can actually produce some fairly simple models where we just flood that topography to see what it would do. This, we vary sediment supply, vary sea level rise. That barge on the left, by the way, is our drilling barge. You want to have an exciting day doing field work. You want to be out on Galveston Bay with 70 feet of drill pipe in the bottom when one of those big tankers goes by with a 20-foot wake. So you wonder what you do. You just tie everything down. We already have it ready to tie down, and you hang on to the best thing you can. So kind of dangerous work, but I never killed a graduate student. I've injured a few, but never killed one. And so we can take those data, and the last thing we do is shoot a line right up the axis of the bay, right up the axis of the old Paleo Valley, because keep in mind these bays are just flooded valleys as sea level rose. And from that, we get something that looks like what's up the upper right there, which is a cross section from basically Galveston Island to the right to where the B is, the modern day Trinity Delta. And the colors represent the different environments. So you start out with the Pleistocene, and then the yellow's fluvial, and then the Bayhead Delta. So this is sort of an offshore progression that you get as you go from the Trinity River out to the Gulf of Mexico. And so as that valley is flooding, those facies, those environments are shifting landward, depositing Bayhead Delta on top of Bay and Bay on top of Lower Bay, etc. And we can, as I've just pointed out, we can recognize those environments using both seismic facies and core lithologies and fossils. And so we can, for example, that flooding surface you see there at the top, the 7,700-year flooding surface with the red line. The red line is actually a core that we punch down to sample that flooding surface. And that's shown there on the far left, that seismic line. And what that's showing is a very prominent surface separating that channel, which is a tributary channel, a very sharp surface, and above that, bay muds with oyster shells. That's a flooding surface. We're going from a Bayhead Delta to a sort of a middle bay environment. And it seems to, at least stratigraphically, looks like it happened pretty quickly. So we've done similar studies with other bays. And in addition to that, we've working with our colleague at Sophie Warney and her students at LSU. She's looked at pollen in some of the cores to try to tell us what the climate is doing over the Holocene. And in general, you can see green there is Corpus Christi area. It kind of stayed pretty constant. It didn't really change very much in terms of precipitation versus Galveston Bay, which shows a pretty significant increase in precipitation. And the slide on this slide here is actually showing on the bottom distance of these flooding surfaces, how far the Bayhead Delta steps landward with each flooding event by looking at planiforms that shift landward. So you can see that in some of these events, like this one, the Bayhead Delta shifted landward 70 kilometers. In other cases, 30, 40, 50 kilometers. And at least during the early Holocene, these events were fairly common, these major flooding events. Those are the events we think are associated with those pulses of sea level rise that I showed you earlier. So that might be what we might expect from something like the Doomsday Glacier collapsing and increasing sea level 30 centimeters within a few decades, just by itself. There's also longitudinal bays, which are an important part of the coastal system. They're very different from these Bayhead Deltas And you hear a lot of people say, well, the sea level goes up, coastal environments will simply migrate landward. Ain't going to happen, thanks to the intercoastal waterway and thanks to the fact that we have this old paleo shoreline, the Ingleside paleo shoreline. There in East Texas is pretty far inland, but by the time you get over into Florida and Alabama, the modern coast is perched up on the old Ingleside shoreline. There's a dramatic change in gradient there. Same thing for Central and South Texas. That red line shows the Ingleside paleo shoreline, and it's about a 1 to 2 meter increase in elevation very quickly. So that's going to prevent these longitudinal bays and the important seagrass beds that are a major part of their ecosystem from migrating landward. And it's the reason why the folks down in Port Aransas are telling us that those seagrass beds are disappearing very quickly. Okay, how are we done on time? I haven't been. Okay. Didn't even notice when it started. I'll be done in about 10 minutes here. Okay, so wave-dominated environments, they're the hardest to deal with. Barrier Island, what they're doing, because there are so many variables that control how barriers respond to various forcings like sea level rise, sediment supply, et cetera, et cetera. And those variables are listed here. And so if you're a modeler and you're looking at sea level effects on shorelines, you have about 12 different variables in your equation that you have to deal with. So it's not simple. But one thing we know for sure is that if we look at the Gulf Coast, these are all maps that are produced by different states, with the exception of Alabama. My home state's a little slow in getting off the blocks there. But they're showing rates of erosion. If you can see the numbers, you see that, for example, in Texas, sort of an average rate of erosion is about 1.5 meters per year, 5 feet per year. That's some places it's 6 feet, and some places it's 3 feet, but it varies quite a bit. Same with Louisiana and Mississippi. The barriers are actually migrating laterally. That's called lateral accretion. And so, but they're moving at very high rates. Florida, their maps suggest that most of their coastline, which is shown in red here, is in what they consider a critical state in terms of current rates of shoreline erosion. So this is not just happening in Texas, it's happening everywhere. We can actually look at rates of shoreline erosion in the past, just like we did in the bays, by looking at beach ridges and dating those ridges. Those ridges are formed during when the barriers are prograding, or growing seaward, and dating washover deposits that occur when the barrier is migrating landward. And so using these data and coupling them with offshore cores, and we've collected sediment core transects from the Louisiana border all the way down to the Mexican border, dozens and dozens of transects that we've collected. And what the upper left is showing there is that these beach ridges, we can actually measure by dating the ridges the rate of seaward growth, progradation. And if we go offshore, we can see that in the form of upper shore face deposits prograding out over lower shore face, et cetera. So we can use these types of data in the same way we use bays. This just shows the upper Texas coast, Bolivar Peninsula, Galveston Island, Follis Island. And it shows that in every case, these barriers had a history of growth, progradation, right up until basically modern times, recent historical time for sure. The rate has varied a bit, but they all have a history of growth. And the exception here would be Follis Island, which is actually aggraded, but it's been fairly stable throughout most of its history. These barriers are all now retreating at rates of anywhere from 1.5 to 3 meters per year. So how far back does that go? We've looked at all the barrier islands in the Gulf Coast where people have done both onshore and offshore work. And I'm not even going to attempt to explain this figure when we published recently last year. And it just shows basically the history of progradation of all these different barrier systems during the late Holocene, followed by erosion, which is shown in red during modern times. So we take all this data, we put it together, and we say, well, what can we come up with a map that shows sort of hazards, geohazards map? The USGS has actually already done that, and we don't think their map, well, their map is not quite as up to date as ours because they're not looking at the Holocene record. This is strictly changes that are occurring today. But what this map shows is that if you look at the red area, which is areas that are currently experiencing sort of critical rates of change, that includes most of Texas, with the exception of the Central Texas coast. And Florida's not quite as bad off, but again, their relative sea level rise is slower, and they have more sand coming into the system. What are we doing? Well, there's one of your Texas legislators on the right. We've tried everything in Texas. It's like like you could write a book. I haven't written a book. But on the left here are literally dunes of straw. And you have a certain cartoon book when you read when you were a child. And that lasted about 6 months until Storm Francis, or Tropical Storm Francis, came along. Then they put these horrible looking geotubes on the beach, covered them in sand, charged the taxpayers for that by saying that's a dune replenishment project. And so that lasted a few years till Hurricane Ike took those geotubes and shoved them right up there, you know what. And the same thing happened in Bolivar, by the way. A lot of damage to homes in Bolivar from the geotubes that were rolling landward. In Louisiana, they have what's called the Mid-Victoria Sediment Diversion. That is a project that will, if it's successful, will potentially save about somewhere between 12 and 16% of the wetlands that will be lost by the year 2050. Multi-billion-dollar project. In Florida, the Everglades, you've all heard about the Everglades problem. Their problem is directly created by humans by diverting the natural drainage system shown on the left to the current day drainage system and diverting sediments away from the wetlands. Here in Texas, we have the Ike Dike. You've all heard about the Ike Dike. Every now and then the media gets on Ike Dike. It's probably the worst idea we've come up, even relative to Stry Dunes. The original plan called for raising the current day seawall up to 15, maybe 17 feet, depending on which version you go with, and extending it for 43 miles along the Galveston, Bolivar Peninsula coast. To accomplish that was going to take about 20 to 30 years, already 10 years behind, just in doing feasibility studies since Ike Dike was proposed. It was going to take about 39 million cubic yards of sand, which is about the volume of sand that currently makes up the entire East Coast coastal lithozone. So you're like having to dig up, Galveston Island to basically get that volume of sand. And the Corps of Engineers, despite what they tell you, they have no idea where that sand's going to come from. They talk about Sabine Bank. Mark Thomas worked on Sabine Bank with me and can tell you the sand there is about 1 meter thick. And it's about 2 kilometers wide and about 10 kilometers long. There's no way you're going to get 30 million cubic kilometers or meters of sand out of something like that. So the Corps has a major problem. They haven't been able to deal with that problem. I don't think they're going to be able to deal with it. They've caught so much flack that they renamed the project. It's now called the Enhanced Dune Project because people didn't like Ike Dike. And it calls for, putting some locks down at the entrance to the channel. But in order to really solve our problems, I'm not going to leave you with a totally negative view here. Actually, our work began back in the 90s and was funded by a consortium of oil companies, all the major oil companies, to look at sand resources out here on the Texas shelf as analogs for reservoirs. Well, it turns out here 30 years later, we're like, wow, that may be one of the most important things that came out of that was the discovery of these deltas out on the shelf and the sand bodies that are associated with those deltas. Now it's not all quite that, I don't want to be that optimistic because we have the Texas mud blanket, which is a blanket of mud that comes from the Mississippi River and drapes our shelf in up to 50 feet of Holocene mud. So we have that to deal with. But there are locations like the Colorado Delta here where sands occur within 1 or 2 meters of the seafloor and could be extracted using hopper dredges like the one shown there. Again, what's the state of Texas done? Well, every state is required to issue a plan like this one, and Texas has been dragging their heels along with Alabama and most states. This is the conclusions, and I'll let you read those, and I'll go ahead and see if there's any questions.